Alright, I finally finished Advent of Code day 22. So in this one, you're given some ranges, and either turn that range on or off. So these represent cuboids. And so for part 1, you only care about cuboids that are in the range -50 to +50 for x, y, and z. So for all of the numbers in the input, you can constrain them to those ranges. So here's my code for that here. And then we just sum up all of the values inside of there, or all of the trues, rather. Part 2, things get a little bit more interesting. So we use the same ranges, but this time it's not constrained, so there's no way you can brute force this. You can't just range from 15,000 to 70,000 times like 70,000 times like 84,000 plus all these other ones. Like, that's way too much. So you need to find a better way to do this. So the way I did this, I used a few classes that I made. First I made a side. This represents like the dimensions of a cube. So a cuboid is made up of sides. I'm using the data class annotation. That makes it so that I don't have to make the init method. It does that for me. Like, I just say it has a start and a stop. It's kind of similar to named tuple, if you've seen that before. And also print it out in a nice way. So with side, we can check if a side encloses another one. And we also have if it overlaps another side or not. So we use those down here in a second. So for the cuboid class, we can check if a cuboid is inside of another cuboid. That means it's like totally contained within on all 3 dimensions. Calculate its volume as you'd expect. That was one thing that was kind of weird about this problem. When they say, like, for example, 10 to 12, that's actually 3 spots. So it's not like grid lines, it's like the cells inside those points. So this is really a 3 by 3 by 3 cube, not 2 by 2 by 2 like you might think. So when I read in the input for part 2, I account for that and I just add 1 to the higher bound. That basically constrains it to be in a grid format. And so it makes everything easier. So we calculate volume as you'd expect. Intersects, this is like, does this cube intersect with this other cube? So that's only true if their x's overlap with each other and their y's overlap and their z's overlap. So this gave me some trouble for a while because we had to go through and say, like, is it equal or not equal? So I added this part eventually. Because this is the case when it's just like on top of or next to, but not actually inside of the other cube. That's what was screwing me up for a long time. And then also we can get the bounds. So what this does, to split up the cube, like let's say we have a 3 by 3 by 3 cube that is supposed to be on, and we're supposed to turn off the center cube. So that would kind of destroy the 3 by 3 by 3 that we have. So to fix that, what we do, we go through for each side in each of those cubes. So like we compare their x's against each other and the y's against each other and the z's against each other. So the situation I just said where there's like a 1 cube inside of a 3 by 3 by 3, then that is the case when you enclose the other one. We're supposed to remove stuff from inside of ourselves. So in that case, for each dimension, you're making the separation. So it's like the part to the left of this. So if we kind of draw this out here, if you have a point, like here we'll use A to A, and then you also have, let's say, B to B. So if A is self, B is other side, then you can just think about this stuff in one dimensions, and then you find all combinations with all the dimensions. So for example, in this one, they intersect with each other, but it's not totally enclosed. So that would be down here. We want to look at the other side where it stops. So that would be here, and where it starts, that's here. And you only want to look at the ones that are greater than our start side. So that happens to be both of them in this case. You're gonna find the lowest one that's after our start. So that's this point here. And so in this situation, we would split up A into this section here and this section here. It's kind of annoying that VS Code highlights both, but so that's two sections that we'd split A into for later, because we're basically cutting off this section. So we would only actually care about this section later, but we have to keep both because for the other dimensions it still matters. So the other situation is when you have something like this, where B is totally inside of A. So in this case, we enclose the other one. So we want one section from here to here, another section from here to here, and one from here to here. And we do that on every axes and multiply or find all combinations of those essentially. So in our example with the 3 by 3 by 1, or sorry, 3 by 3 by 3 with the 1 inside, then if the 1 is in the center, then you're going to split up the 3 by 3 by 3 into all 1 by 1 by 1s. And you'll find all 27 of those, but then you don't want to keep the one that's the exact same as the other shape. So here we use this down here. So when we split up a shape, that's what we're doing. This is also like you can think of it as subtraction, like the 3 by 3 minus the 1 by 1, which is why I have the subtraction overloading here. So you can think of it this way. So first of all, if we are inside of the other cube, so let's say you have like a 3 by 3 and then like a 100 by 100 is turning everything off inside of it, then you just like delete this cube basically, so you want to return nothing is left. But if we don't even touch each other, then it's like our current cube is not affected, so we just return ourselves. Otherwise, we must be touching. So we go through the get bounds for each side, and so we get split up, but then we want to eliminate the ones that are that are inside of the other one. So that counts for the fact of when they're the exact same. So we want to get rid of those. So in our example, when we split up into 27 small cubes, you would want to delete the center cube because that's the same as the one that we were trying to delete. And we return all the pieces that we've been split up into. So here's where we actually do this. This is just for debug purposes. So we have all the cubes that we've seen, like all the pieces. So on the first iteration, like we don't have any yet, so you can just go ahead and add it. It's not going to interfere with any other ones that we've seen so far because we haven't seen any. And then let's say we do have some cubes already. So for each one of those that we've already seen, let's say I'm about to turn off some of the cubes, then we want to think about this existing cube that was already inside of the cubes that are on, subtract out the cube that we're trying to add in. So you do this even if the new section that you're turning on, is turning on cubes compared to turning them off, because you don't want to double count a section, like overlapping 3 by 3 cubes, and those would count twice, which you don't want. And so with the way subtract works, basically like deleting the original either way, but then we add it back if they don't intersect, for example. So if the list does not exist, or oh wait, oh yeah, this was also for debug purposes, but we don't need this anymore. It was to figure out where things were going wrong. Alright, so once we get down here, it's like we've already subtracted the new cube from everything, but if that cube is supposed to be on, then it's like add that new region in. But if it was supposed to be off, then it's like, well, you subtract it from everything, but you don't do anything after that. And then we just reset for the next iteration up top. So if we run this, surprisingly, it runs faster with Python instead of PyPy. So if I run this here, then double check it's still correct. Yep. Yeah, there's 420 lines in my input. And yeah, it's a really large number. There's no way you can brute force that even with C++ or something. Well, I don't think so, at least. So that is day 22. Thanks for watching.